reactions can happen everywhere. Let's imagine molecules as people in a city. Say two persons now bump into each other, and one person's arm got severed and reattached to another's nose. Even after this terrible incident, life still goes on in the city. This is just an example of chemical reaction. Chemical reactions can happen in many different ways, like two molecules join and become one, or one split apart into two. Two key conditions are important is that these two must bump in the correct direction, and speed is needed for the reaction to happen. Some reactions cannot be reversed, like iron rust, milk goes bad, or people getting old. But most reactions are reversible. Arms can be reattached when they bump into each other again. If we zoom out and look at the numbers, we'll see that at first the number of people without arms and additional arms will increase. But as time goes on, the number of people in each state will reach to a constant, creating an equilibrium. If we draw it into a diagram, we'll see that the number of limbs transferred per second forward will start high and then fall, while the number of limbs transferred per second backward will start at zero and then rise. Let's look at an example where nitrogen and hydrogen combines to form ammonia. As we can see in the diagram, as nitrogen and hydrogen react to form ammonia, the concentration of those gases drops, making them less likely to collide and keep reacting, so the rate of the forward reaction slows down. At the same time, the concentration of ammonia rises. More ammonia molecules are able to break up into reactant gases, and surprise, the rate of a reaction speeds up. Eventually, those two processes reach a point where they have the same rate. Notice that in an equilibrium, the reaction is still happening, but you will not notice any change, because changes will be balanced at that point. Scientists are just not happy that everything is tranquil, so they decided to mess things up, and this is where the Le Chatelier's principle comes in. He finds that when a stress is placed on a system at equilibrium, the system will proceed in a direction that minimizes stress. Imagine that people are now bumping in a hall. When the nitrogen concentration increases, in this case more people are filing in, there will be more people for hydrogen to play with, increasing the forward reaction rate. The reaction will then continue to happen until equilibrium is reached. Now let's look at what pressure will do to this reaction. From the equation, we can see that as a whole, 4 moles of gas produces 2 moles of gas. So the forward reaction decreases the volume while the reverse reaction increases it. Increasing the pressure will put more pressure on the high volume reactants than the low volume products, increasing the forward reaction. We'll now look at this interesting equation involving two different ions of cobalt. One of the ion is pink and the other is blue. If we add hydrochloric acid, the reaction will shift right and then turn blue, while adding water will push the reaction backwards, turning pink. Another way we can change the state is to change the temperature. Raising the temperature is like adding a reactant called heat, causing the reaction to be pushed right, while lowering the temperature will turn the solution from blue to pink. These reactions can go back and forth many times. Equilibrium is not about being the same all the time. It's just about keeping your balance as your circumstances changes. Gene pools and highway traffic actually shows the same pattern. You just need to zoom in to see it.